Welcome to Dr. Judd's Continuing Calculus video series. Today's lesson is section 5.6 from Rogowski, which is known as U substitution. U substitution is not so much a rule, but a concept. It's a practice to help make some integrals easier to make messy integrals look a little easier and easier to use. So we'll do that, and we'll show lots of examples. But honestly, this is something you're going to have to practice on your own too. There are too many possible variations and nuances to it to go through all of them in one video. So we'll take it as we go. The idea is the chain rule, but backwards. Remember, integrals are antiderivatives. So if the derivative of the chain rule looks like this, what we're going to say is the antiderivative of this is that function. So let's take a look at it. Notice I'm writing this as an indefinite integral. Indefinite integrals, definite integrals, it works for both of them, but I'm not going to write the endpoints because I don't want to right now. But I can, and we will. F prime of g of x times g prime of x, the integral of that dx is f of g of x plus c because it's an indefinite integral. But this is messy, so what we often do is we substitute a new variable, not x anymore, but we'll substitute in a new variable. So we're going to call this right here u. And that makes this the derivative of u. So that whole thing is called du. And we make a new integral. That may or may not make sense yet, but let's do an example, and hopefully it'll start to make sense. So what are we looking at over here? Our first example, the integral of 2x e to the x squared dx. Hopefully, if you think about it, knowing that we're doing chain rules, you can kind of guess what the answer is. But what we're really looking for is, I'll step back for a second, what we're really looking for is a function whose derivative has something inside of it, and then something else outside, which is the derivative of that. So come back. We're looking for a function inside somewhere that has its derivative outside. So this is the function inside. So what we're going to do is call that u. So what we need is the derivative of u. There are many ways you can write this. Many people like to write this as du dx equals, so that's the derivative using not the Newtonian but the Leibniz notation. But I prefer writing it as du equals, well, the derivative of u is 2x, but it's not 2x because it needs a dx on it. Du, and think about it, du dx is that. So I'm going to say the du itself is that. Now the question is whether that's in our integral already, multiplied in. It has to be multiplied in order to work. Do we have that? We do. Right here's part of it, right there's part of it, all multiplied together. All of that makes our du. So I can substitute all of that out for a du and substitute this x squared out for a u. This is then equal to the integral e to the u du. So how does that work? Well, that integral now, u, is our new variable. This is where the dx, the du, whatever this is, where this piece becomes critical. You kind of could ignore it now for a while, but now we can't ignore it at all. This is now our variable. What's the antiderivative of e to the u if u is our variable? Well, it's e to the u, plus c, of course. But we're not done, because our question originally was in terms of x. We're almost done, because what is u? U is x squared. Now we're done. That is the antiderivative. And if you take the derivative of that, using the chain rule, what do you get? E to the stuff, the derivative is e to the stuff, times the derivative of the stuff, which is 2x. So we get e to the stuff times 2x. It works. Let's do another indefinite integral before we move on to what happens to limits. So here's another one. We're looking for a function that has something inside of it, and an outside piece that could be its like derivative. Hopefully you can see. The inside, which we're going to call u, well, what's inside? This is. U is sine of x. Du, then, is the derivative of that, which is the cosine of x. But not just cosine of x dx. So this stuff is our du. All of that together is the du. So what is this integral? This is the integral, square root. I'm not going to fill in what goes in there yet, but the stuff that's inside is our u. Now, integrating the square root of u, that's a little awkward. And I chose this one because square roots are always kind of problematic. So let's rewrite this again. Not another u substitution, but just write that. That's u to the 1/2 du. That's the same thing. So now the power rule says if you're going to anti-differentiate that, add 1 to that. That makes it 3/2. So we get u to the 3/2. But we need 1 over that outside to cancel out for when you take the derivative. 1 over the fraction is the reciprocal fraction. And this is an indefinite integral, so you do need that plus c. It's important. There are examples which show that if you forget the plus c, you can do the integral a couple different ways and get different answers. But we're not done again, because the integral was originally in terms of x. So we have to substitute back. We get 2/3 of the sine of x to the 3/2 plus c. And that is how you do u substitution. Hopefully those two make some sense, but let's do a couple more just to get a feel for them. Here's an uglier one. This one, hopefully you can still see, there's something inside. Now, there's a couple ways we could do this. There's a pi. We could get rid of that pi. Well, you know what? This is the whole thing inside. That's probably the most sensible way is to do that. Let's let u equal pi square root of x. What's u? Well, the pi stays there because it's a number. But the square root of x, the derivative of the square root of x, we've done this before a couple times. That's x to the 1/2. So its derivative is 1/2 x to the minus 1/2. But I want to write it in terms of square roots. So it's 1 over 2 square root of x dx. Why the dx? Because du has to have a dx over here once you're done. Now, do we have that? And the answer is no. We're kind of in trouble. We have parts of that. So let's work with the parts we have. I need a 2 on the bottom in order to make this work. I can do that. I can put a 2 down here. That's cheating, though. If I put a 2 on the bottom, I've changed it. Unless I also put a 2 on the top. I also need a pi. I can put a pi on the top. No problem. As long as I put a pi on the bottom also. So, now I've got all the pieces I need and a couple little extra things. What is the du? It's got this pi in there. It's got this 2 square root of x. It's got that dx. That all is our du. Now, those are numbers. I'm going to keep them. That's our u. So I'm going to integrate. I've got 2 over pi times the cosine of u du. Now, is that right? Cosine of u, that's all the du and those numbers. The numbers can come out, and they will in just a second. But I want to talk about these two things. I have 2 options. Well, I have 3 options, but the third one's wrong. I could just keep the 4 and the 1. That's the wrong option. The second is I could ignore it for the moment and just go through everything. At the end, once I'm back to x's, I could do that. That's the option I'm going to use here. But there's a third option. U is equal to this. These are x's. So I can turn them into u limits. I'm not going to do that right now, but I'm going to do that in my next one. So I'm going to pull these numbers out right here. I need to anti-differentiate the cosine of u, u being our variable. The antiderivative of the cosine is the sine. You have to think about those sometimes. And now plus c, but this is going to be a definite integral ultimately, so the c will cancel out. So, what is that? It's 2 over pi, the sine of, what is u again? Pi squared of x. That sounds hideous and horrible. It's not as bad as it looks. Because, why? Because the 4 makes that 2. So we have the sine of 2 pi. The 1 makes that a 1, makes it 1 pi. So this is 2 over pi the sine of 2 pi minus the sine of 1 pi. Both of those are 0, and we get 0. Let's try another here. Well, here it is. Hopefully you can see there's an inside thing. The inside is right here. Sometimes it doesn't work nicely, but in this case, that's our u. If that's our u, well, that means our du is the derivative of that. Derivative of x to the fourth is 4x cubed with a dx thrown on because we need it. Do we have that? The answer is no. We have most of it. We're missing a number. Missing a number is rarely bad. Why? Because a number you can multiply and divide easy. Everything else is trickier. There are some cases it works, but everything else is trickier. I'm going to multiply by 4. I'm going to divide by 4. Doesn't change anything. But it gets me my du right here. This is the du. Drawn kind of weird, but there's a 1/4. E to the u du. So make sure that's the du. That's e to the u. There's the 1/4. Now, as I said before, I did everything, and at the very end, I substituted back for x limits. I'm going to do something different this time to show you sometimes it's nicer to change your limits. This is an x limit. If I'm in u is x to the 4th. So what is that to the 4th power? It's 7 times 7 times 7 times 7. I think that's 2401. It's 7 to the 4th. In any case, right? Why not minus 7 to the 4th? Well, minus times minus times minus times minus is plus. What's this? This is also 7 to the 4th. Look at that. These are the same. And while we can do this integral, you should also notice that we have a rule that when this and this are the same, it's 0. We save time sometimes by substituting in the new limits and canceling things out. Let's try one more just to see how it works. Tangent of x. Why? Because we've never been able to integrate this before. It doesn't have a nice antiderivative. And it doesn't, because what is the derivative of the tangent of x is the secant of x squared. But the anti not so much. So let's rewrite this as the sine of x over the cosine of x dx. Now, hopefully, by now, you can recognize that one of those is probably going to be like our u, and the other is going to be a du. But which is which? Well, let's step back for a second. Where was the du? It was here. It's multiplied on. Step back one more. Where was the du? Well, the du, which is all of that, had to be multiplied on. It just happened to be at the bottom there. The du has to be multiplied on. So this is going to have to be part of our du. That means that's our u. So if u is the cosine of x, what's du? Du is the derivative of that. It's minus the sine of x dx. That will work. Except we don't have the minus sign. So now we do. That is our du. We have a minus. Minus 1 over cosine is our du. And I can plug these in. The cosine of pi over 6. The cosine of pi over 3. Cosine of pi over 3 is 1/2. The cosine of pi over 6 is the square root of 3 over 2. Correct me if I'm wrong. I think those are right. This is a nice little one. It's got an antiderivative of the natural log. This is the natural log of u. Evaluated at 2 different spots. I'm running low on time, so I'm just going to end here. We can plug in and evaluate. Hopefully, this makes some sense, but you're going to have to practice it. Until next time, this is Dr. Jet.